Hello everyone, this is Vasant, a 9-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss about stress strain diagram. This is the third lecture on stress strain diagram. So in previous lectures, we already covered up to OB region, right? So we already covered up to O2B region. O2B region, the material behaves as elastic, right? Elastic means on removing the load, it will regain its shape and size, right? So in the same direction. In that part also, OA is linearly elastic, right? It is linear. And in portion AB, it is non-linearly elastic, right? So this is non-linear. So in portion OA, we define Hooke's law, right? So in general, while solving civil engineering problems, we generally take Hooke's law into consideration because we generally design elements for linear elastic deformation only. So now let us go to part B. First, we are increasing the load gradually. So the stress will increase, the nominal stress will increase gradually, right? So it will increase gradually. So after certain stress, the material will become somewhat weak. Means after removing the load also, it will be unable to regain its shape and size. So it reaches a plastic deformation. It is known as plastic deformation. In plastic deformation, the material will have permanent deformations. Means it is unable to recover its deformation on removing the load. Okay, why it happens? See, first it will be linear, it will be elastic, so it will resist the deformations effectively. But after gradual increase of the load, after certain stress, the material will undergo permanent deformations. So that is because of a plastic flow. See, we already discussed that the maximum shear, we take a rod. What is the plane of maximum shear? The plane of maximum shear will be like this, right? 45-degree plane. And the shear stress, the shear stress in this plane will be like this. The shear stress in this plane will be like this. The shear stress in this plane will be like this. The shear stress in this plane will be like this, right? If you consider these two things, it is trying to move the particles in this direction. And if you consider these two forces, it is trying to move the particle in this direction. So it is responsible for plastic flow. So the material will undergo permanent deformations. Permanent deformation. More the plasticity, more will be the permanent deformations. So if you consider a mild steel, this is a stress strain diagram of mild steel actually. So it will act as almost perfectly plastic. Means whatever deformation happens in BC region, that will be permanent. Means there will be no elastic deformations for elastic deformation part in the deformations. Okay. So in BC, if your material is perfectly plastic means permanent deformations. One more thing is that if material behaves as perfectly plastic, then you know means there is no need to apply the stress. We already applied this much of stress. After this stress, there is no need of increasing the load. It will automatically deform. See, without increasing stress, it is deforming. Without increasing stress, it is deforming, right? And if you observe, initially the slope is like this. Now the slope is becoming like this. Now the slope is becoming like this. So from O to C, the value of E is reduced, right? Because slope is reduced, means the resistance to the deformation is reducing as we increasing the load gradually. Okay, so up to C. So this is about plastic deformations, and this phenomena is also known as yielding. means elongation without increasing the stress is known as yielding. Okay, so this is about portion B. In portion B there will be plastic deformations. Plastic deformations will have some permanent deformations. If your material is more plastic, then there will be more permanent deformations. So if your material is perfectly plastic, then all deformations will be permanent. Permanent means they will not recover their deformations on removal of the load. Okay, so and from O to C we observed that in the diagram the value of E is getting reduced, means the material is getting weak, means the material is unable to the resistance, the ability to resist the deformations is decreasing as we go from O to C, right? So now let us move to C to D. We said that O to A initially the material will resist effectively, after it will become weak, but how of sudden it is now increasing its E value, means first O to C the value of E is decreasing, but suddenly the value of E is getting increased. How this is happened, means this is actually known as strain hardening, means it is becoming hard to strain the element. Why this is happening all of a sudden? Already material became weak, but how this happened that the value of E is getting increased again? So that we need to know now. That is about region CD. Region CD is known as strain hardening. So we already said that E value is decreasing from O to C, means material become ability of materials resistance to the deformation is decreasing as we move from O to C as we increasing the load. But now on increasing the load, if you see over here, on increasing the load, the value of E is increasing right here initially, right? So how this is happening? This is because when we are solidifying the metal to form actual metal, so in that metal there will be some defects. One of the defect is known as edge effects. Okay, means if you consider a block, the atoms will be something like this. Okay, in some parts the bonds are not completed, means the bonds are incomplete, the materials are incomplete, so those are known as edge effects. So if we draw like this, in this portion there is no bonds, right? So when we apply shear stress, we are applying shear, right? So we are applying shear. So we are trying, see these particles will try to move here, and these particles will try to move here, and these particles will try to move here, here, here. So what happens? This whatever edge effect is there now, that will move. Means this is dislocation of the edge effects. Means the movement of the edge effects. Means now what happens because of the shear stress? Initially the edge effect is here. Now if you consider initial position is this. This is 1. This is position 1. This is position 2. So the position 1 will be here, and it will go to position 2 dash, and new bonds will form at 1 dash, and now position 2 is here, right? Now edge effect is moved here. So because of the movement of the edge effect, the material will regain its stiffness. Okay, so how, means you said that okay it is regaining the stiffness, but how, why after some time it is again decreasing? So that is because of, we already said one point, you know about grain boundaries, right? We already discussed about grain boundaries. So these edge effects can move only in their colonies, right? It can't move over the one colony to another colony. So when it reaches the boundary, it will stop, right? Up till that point, the material stiffness will increase. After that point, the material again decreases its value of E on increasing the load. Understand? So grain boundaries is the region. So up to until certain stress, the value of E will get increased, right? So this is grain boundaries. This is about strain hardening. In strain hardening, because of the movement of the edge effects, the value of E will gets increased, right? So because of the increasing rigidness, increasing stiffness, the increasing strain will become hard, right? To increase the strain, we need to increase uh more sigma, right? See, if you see over here, if you increase here to here, suppose this is 1 unit, okay, the increasing strain will be this much, right? So, but same amount if you increase over here, the epsilon will be this, epsilon dash. So, epsilon dash will be less than epsilon. Do you understand? Means on increasing the same amount of stress, the value of strain will be less in the case of strain hardening, in the portion of strain hardening. So, this is about strain hardening. So, the material after certain means you are going to you are increasing the load gradually. After certain time, the stress, whatever stress developed in the material will become ultimate. After that, if you increase small amount of stress, then it will going to fail. Means this is about point. So this is we are talking about point T. Point D is point of ultimate stress. If you increase a little more load, then the material will fail. So this is sigma max, right? So this is sigma ultimate is equals to sigma ultimate. So if you take the value of strain at this position, this is E value. So this is not maximum. This is not maximum strain. We said that in the stress it is maximum, but it can also elongate. मरते मरते हुए भी वो elongate कर सकता है थोड़ी देर तक. So for to understand those things, we are again going to decrease the load. We are again going to decrease the load, because if you increase the load, it will fail. Then we are unable to understand the elongation. How much elongation will it consider, right? So to understand those things, we need to decrease the load, because if you increase the load, it will go above the ultimate stress. Then the material will fail. But we need to understand when the material will fail in elongation, not in stress. Okay. So to understand that, we need to again decrease the load, right? So when we decrease the load, the material will again elongate. So now the E value will get this. So it will elongate up to certain amount. After that, it will fail. Okay. Then this will be E max. So E max and sigma max are at different positions. So this is about region D. In region D, necking will happen. What means necking? See, one thing we forgot is that when you are elongating the material, so it will decrease its area, right? So after certain time, the area will decrease that much, then it will form like this, then it will cut. So it will cut in cup cone shape. So that is known as necking. It will fail at 45-degree plane. So what is the reason for failure of necking? The necking is mainly because of shear stress, not because of tension. Okay. So shear is responsible for necking. That is the reason why it is failing at 45-degree plane. Because at 45-degree plane, there will be maximum shear stress. If tension is responsible for that, then it should fail at perpendicular, right? In this direction, it should fail like this, right? But it is not failing like this. It is failing in 45-degree plane. So, and what about maximum stress and maximum strain? Maximum stress is this one. This is sigma max, and maximum strain is E fracture. So E fracture will be is equals to E max. Okay. And what is the measure of ductility? See, from this diagram, you can understand that in ductile materials, the elongation will be more. Means it will elongate after elastic limit. It will elongate more before failing. Okay. So this region represents the measure of ductility. Okay, so if this region is more, then it is more ductile, means before failing it will elongate, means it will give signal. If you use ductile material in a structure, before failing it will give you some hints that I am going to fail, I am going to fail. But in case of brittle materials, that doesn't give any signal, it will suddenly fails, that we will deal in next lecture. So this is about ductile materials, and this is about the stress strain diagram of a ductile materials. But if you see over here, there is a dotted diagram. So why we drawn like that? That is actually true stress strain. If you consider true stress, then the diagram will be like this. Now question arises, what is true stress? That also we will deal in future lectures. We will understand in detail. So with this, we end today's lecture. In next lecture, we are going to discuss some more concepts on stress strain diagrams. Thank you.